Ladies and gentlemen, good morning, good afternoon, and good evening. Welcome to this IFRR Colloquium on Fukushima 10 years after. I'm Hajime Asama from the University of Tokyo of Japan and the moderator of this colloquium. First, I'd like to introduce the scope and abstract of this colloquium. The Great East Japan earthquake and the tsunami that occurred on March 11, 2011, caused the serious accident of the Fukushima Daiichi nuclear power station of Tokyo Electric Power Company, TEPCO. This level 7 accident is one of the most serious nuclear disasters in the world. The Japanese government and TEPCO decided to decommission it. It is, however, a very long-term mission, and it is predicted to take at least 30 to 40 years. Over the past 10 years, various robotics and remote technologies have been introduced at the Fukushima sites for various tasks, showing success and revealing challenges. Successful decommissioning will rely on development of highly reliable robotic technologies that can be deployed rapidly and efficiently into the sites. The discussion will focus on the decommissioning challenges and the robotic technologies that have been used in Fukushima. Then I'd like to introduce the panelists and the front row briefly. These are the list of panelists on the front row. First, I'm Hajime Asama, moderator and one of the panelists. I am a professor and director of research into artifacts Center for Engineering of the University of Tokyo. I earned Doctor of Engineering from University of Tokyo in 1989. My research areas are service robotics, distributed autonomous robotic systems, embodied brain science, and so on. I am an expert member of Council of Decommissioning of Fukushima Daiichi Nuclear Power Station of Japanese Government and TEPCO, and a member of Expert Committee on Fuel Removal of Nuclear Damage Compensation and Decommissioning Facilitation Corporation. Currently, I am a council member of Science Council of Japan and president of IFAC. The second panelist is Professor Shunichi Suzuki. He is a project professor in the Department of Nuclear Engineering and Management at the University of Tokyo. He graduated from the University of Tokyo in 1982 and joined the TEPCO. After the Fukushima accident, he has engaged in the design and installation of the contaminated water treatment system and R&D management partly as a general manager of International Research Institute for Nuclear Decommissioning, IRID. Since 2015, he has been working on various research projects on retrieving fuel debris, waste management, and human resource development related to Fukushima decommissioning. Third panelist, Dr. Matt Miller. He is the CEO of Createch, which works in the civil nuclear, defense, rail, aerospace, security, and medical sectors. Its technology has been used to help investigate and clean up the Fukushima nuclear station in Japan. He started his career as an academic working in research and development at Oxford University, and he won many awards and holds 2 Quince Awards. The last panelist is Dr. Gil Pratt. He is the CEO of Toyota Research Institute, where he directs research to create new capabilities for Toyota in active safety, automated driving, robotics, and other human amplification technologies. His academic research focused on robotics and intelligent systems. He earned Doctor of Philosophy in 1990 in electrical engineering and computer science from MIT. He was an associate professor of electrical engineering and computer science and the director of the LEG lab at MIT, and a founding professor of electrical and computer engineering and associate dean of faculty affairs and research at the Franklin W. Olin College of Engineering. He served as a program manager in DARPA from 2010 through 2015 and led the DARPA Robotics Challenge and so on. And we have 4 people for front row. Professor Robin Murphy, Texas A&M University in the United States. And Dr. Philippe Bidot, CEA, France. And Professor Keiji Nagatani, University of Tokyo, Japan. And Dr. Jennifer David, Bristol Robotics Laboratory in UK. And Dr. Emiko Uchiyama, Taitech, Japan. Then I'd like to start with my presentation on the story of the accident and the robot technology utilization at the sites. What happened in Fukushima? As I mentioned, the Great Eastern Japan earthquake and tsunami happened in March 11, 2011. And the tsunami attacked the east coast area of Japan, and it totally it brought a very huge damage in this area. These are the number of the people who are dead and missing. Another serious issue was the accident of Fukushima Daiichi nuclear power station. So this is the story how it happened. After the earthquake, scrum was successfully done, which means that it stopped the criticality reaction of the reactors. But after that, tsunami attacked this nuclear power station, and all the fuel tanks and the generators were damaged. Then a station blackout happened just 1 hour after the earthquake. And all the cooling systems of reactors and fuel storage pool became inferior, and cooling water was lost, and meltdown of nuclear fuels happened. After that, hydrogen explosion happened in 3 units, unit 1, 3, and 4. The location of the nuclear power station is 200 kilometers north from Tokyo. So this is the location. Actually, there are 2 nuclear power stations in these areas, Daiichi and Daiichi. Accident happened in 4 units of Daiichi. So when the accident happened, unit 1, 2, 3 were under operation, and unit 4, 5, 6 were under maintenance. But the hydrogen explosion happened in unit 1, 2, and 4. Just after the accident, Japan, this is the pictures just after the accident. So by the hydrogen explosion, reactor buildings of unit 1, 3, 4 were totally damaged. And just after the accident, Japanese government established special project teams, and I was a member of remote control and robotics team. This is the structure of the plant. So this is a BWR type plant, and there is reactor buildings and the turbine buildings. And the nuclear fuels are located inside of pressure vessel. Nuclear fuels are covered by this RPV, and it is covered by containment vessel, very thick concrete wall, and it is covered by reactor buildings. These containment are all called boundaries. But by the hydrogen explosion, all these boundaries are broken and a huge amount of contaminated materials are scattered in the environment. So this area is called the pedestal. All the meltdown fuel, which is called fuel debris, it's melt and dropped to the bottom of PCB. And what we should do is to retrieve all the meltdown fuels located this area, as well as in the pressure vessel. And also we should retrieve the fuels in the spent fuel pool in these areas. So this is current situation of 4 units, unit 1, 2, 3, 4. As I mentioned before, unit 1, 2, 3 were under operation. So there are nuclear fuels in the containment vessel of unit 1, 2, 3. And we have also some spent fuel in the spent fuel pool in unit 1, 2, 3, 4. But we finished to retrieve all the fuels in spent fuel pool of unit 3 and 4. But the mission is we should retrieve all the meltdown fuels from unit 1 to 3, as well as the spent fuel in spent fuel pool of unit 1 and 2. These are the water level inside of PCB. So as you see in these pictures, in the case of unit 3, the water level is very high. So when we investigate inside of a pedestal area, we need some kind of underwater robots for this unit. So TEPCO issued this mid and long-term roadmap. It is divided into 3 phases. Phase 1 is period to start of fuel removal from spent fuel pool. And phase 2 is period to start of fuel debris removal. And phase 3 is the period to the end of decommissioning. So timeline is 2 years. This is the 2 years timeline, and this is 10 years timeline. And this would be 30 or 40 years. So now we are 2021, so it is a kind of end of phase 2. And but this schedule is a little bit delayed, and we will not be able to start of fuel debris removal until the end of this year. Maybe it will be done next. It will be started from the next year. So these are the needs for the remote technologies: water injection, removal and transportation of rubbles, fuels, and contaminated water, investigation, measurement, and mapping, and sampling of dust or contaminated water or concrete core or fuel debris, the decontamination and shielding, fixing of contaminated water leakages, handling, transportation, removal, setup of devices, instruments, and equipment, and so on, waste and contaminated water management, and dismantling of facilities. So as far as I remember, more than 50 kinds of robot systems or devices were already used at the Fukushima sites. These are some examples of the machines which were developed in other countries. So this is a kind of concrete pump truck construction machines, and there are some ground vehicles, the crawler type robots, and some the aerial vehicles like this and this. So when we use this T-Hawk aerial vehicles, Professor Robin Murphy helped us a lot. These are some machines, robotic machines, which were already used at the sites. These are all developed in Japan. So construction machines and crawler type robots or underwater robots. And also we have this surface robot or specialized robot systems. So roughly, I can divide the stories into the three phases, depending on the missions. Phase one would be a kind of emergent situations. The main mission was cooling down of reactors or site decontaminations. The typical example is the utilization of remote controlled construction machines. So this is a survey map which was observed just 10 days after the explosions. So as you can see in these pictures, there are a lot of hot spots by very high radiation areas. This is the location of unit 1, 2, 3, 4. So all the sites are very much contaminated. So if any of workers walk around these sites, he will be exposed to high radiations. So it is really dangerous situations. Then this kind of remote control unmanned construction systems were introduced and used for cleaning up all the rubbles which were highly contaminated. And it was very successful. And by these missions, the radiation level of the site was very much reduced. Another example is PACBOT. So President Obama gave us 2 units of PACBOTs just after the accident. The TEPCO company used these 2 PACBOTs for investigating inside of PCB. And it was also very successful. And this is the first time we just watched what happened inside of PCB. It was done April 17th, just 1 month after. In phase 2, that is main mission was stabilization. And investigation, containment, system reconstruction, aftershock measures, these are the main missions. So in this case, some of the robot systems were modified and used. This is one example. Robot is called Quince. This was originally developed by for the disaster response by Professor Koyanagi, Professor Tadokoro, or Professor Keiji Nagatani. He is now the one of the front row today. And they modified the platform, a mobile platform, and installed some devices for the missions and introduced to the reactor buildings. And this is investigation mission, and it was very successful. This robot climbs up the stairs to the 5th floor and observed what happens inside. This is a user interface for the operators to operate this robot. The operator can watch all the camera images which was taken by the robot. The last phase was decommissioned. It is a final target. It is really difficult. But in total, reduction of radiation exposure of workers is very, very important missions as a whole. For the field debris retrieval, there are several robots were already developed for investigating inside of PCB. This is a transformer robot, and this is a Scorpion type robot. This is a small ROV, which were already introduced in Unit 1, 2, and 3. This is how the transformer robot works. So containment vessel is covered by thick wall. So when we insert the robot, we should make the robot very small, and then it should be inserted from the pipe, which is called the penetration, with just 10 centimeter diameter. And so when it is inserted, it is like a snake shape. And after insertion, it transforms itself and move around as a crawler type robot. And this is a kind of the telescopic type cameras, which was introduced to Unit 2. And by this camera, this kind of image was observed. And it is very exciting to see what happens inside of pedestal area. So you can observe some structures dropped from the RPV, or some melt, or some deposits, and so on. So the field debris are included in this area. So they introduced also such kind of grippers, and they tried to pick some part up. It was also successful. And this is a story when they insert the underwater robot, small ROV, and it was also successful. And it could obtain this kind of images. And this is another story. This is the dismantling of exhaust stack of Unit 1 and 2. This exhaust stack was used for vent. So it is highly radio contaminated, but it is also deteriorated and very dangerous. So they decided to develop special robot systems to dismantle this exhaust stack. And a company in Fukushima area developed this robot. And it is very interesting structures. This robot has 3 arms to cut the outer structures. And inside, they have some kind of tip saw to cut the stack body. And it was successful. And now they are developing this kind of arm type access device. It will be used for the small scale retrieval of the field debris. It is 22-meter long and a large number of degrees of freedom. And the payload is 10 kilograms. And it is developed in UK, and it is now tested. And hopefully it will be used next year. And there are lots of successful stories, and the robot was successfully used for exploration, investigation, measurement, rubble removal, and sampling. But there are also some unsuccessful stories. Decontamination it is not very much done yet, and water leakage fixing is not successful yet. And we need sampling of field debris in near future, and also we need field debris removal and transportation. So these are some unrecoverable robots. These robots were stacked at the sites. And we should learn lessons from these failures. So these are some factors of failures: communication failures, or misoperation of operators, or malfunction of radiations. But there are some indirect factors, like these robots are just, how to say, prototypes. It is not products, so they are not so reliable. And another big issue is that we should design and develop the robot system which work in unknown environment. And we should consider some kind of measures for these kind of factors. For communication failures, some solution would be combination of wired and wireless communication or implementation of wireless communication infrastructures. For miss operations, we need some kind of training of operators or improvement of human interface. Maybe haptic would be very useful for human interface. But function by radiations, we need some rad-hardened devices, or we can use some kind of mechanical systems, and the design of robust systems by providing some redundancy. And we developed some kind of good human interface. This is bird eye view system for the robots. It is now used in the automobiles nowadays, but we developed this kind of system for the robot systems. And this system is already used for this kind of robots, which were developed by Mitsubishi Heavy Industry. And now these kind of the robot view from arbitrary viewpoints are under development. So you can change the viewpoint. It is very useful for operating the robots. And 3D reconstruction is also very useful from the images. And Professor Nagatani and Professor Tadokoro tested the tolerance of the devices which were used in the robot system for the radiations. And CPU board or CCD cameras or batteries or DC-DC converters, but they found that it's rather tolerant against the radiations. So it can survive more than 100 gray total dose. And for the prototypes, solution could be risk assessment for failures or testing. And this kind of mock-up facility were already built in Fukushima area, and it is now used for testing the robot and also training for operators. And for unknown environment, we should advance investigation, and also we need to assume some various situations when we design the robot systems. So for future, we need a lot of diverse technologies, portfolio of robot technologies, and waterproof devices and radio tolerant devices are also necessary, and autonomy and intelligence for remote control systems would be facilitate the teleoperation. Haptics, 3D reconstruction of images are also necessary. I think so all kinds of robot technology is required in decommissioning. So we need a kind of department store of robot technology. Aerial, ground, underwater, from small size to big size, sensing, mapping, monitoring, sampling, navigation, cutting, manipulation. But currently available robot technologies goods which can used at the sites are very much limited. So finally, I'd like to summarize my talk. So they require teleoperated RT systems. They don't want so much autonomous systems. So we need some kind of distributed system, human interface and communication. But to improve the, easy the operation, we should consider about the situation awareness, and the autonomy will also facilitate the teleoperation. Some kind of autonomy should be installed at the edge. And finally, body consciousness is a kind of psychology will also help when we design the human interface. Okay, thank you very much for your attention. So I should stop now. And I'd like to accept any questions for my presentation first. So do you have any questions? I'd like to encourage front row to ask questions.
I have a question. Thank you.
Yeah, Robin, please.
Thank you for the lovely and very informative talk. What do you see as the major differences between the robots used during the response and are now being used for decommissioning it? Are they different robots? Is it more manipulation, or is it different missions, or is it different operators that are more regular nuclear operators? What do you see are the big differences?
Actually, Fukushima decommissioning is very, very special, I think. And the target is covered by thick concrete and dark and wet and very, how to say, indefinite environment, unstructured environment, and very difficult to access. And in addition, high radiation. It is very, very special environment. And some missions overlapped with disaster response. So that's why we could use disaster robots at the beginning. For example, rubble removal or just investigations. And but when we start decommissioning of field debris, we need very special devices. That would be some kind of difference.
May I ask a question also?
Yes, Philip, please.
Yeah. This is first a comment. 10 years after this terrible accident, I'm not sure that today we would be able to do much better than what we did at that time with robotics systems. And this is the first point. I just want to ask you if you share or not this comment. And I have a question, which is more or less a technical question. What you said is that we are far from having autonomous systems able to evolve in those unstructured environments to do things which are very complex. So we have to find a sort of compromise in between teleoperation and autonomy. And this adjustable autonomy seems to be a very challenging question, even for research. I would like to hear your comments about those 2 points.
Thank you very much for your question. So the difference between 10 years ago and now is that when the accident happened, they look for the robot system they can use, but it was very much limited. So they just, how to say, procure all the, how to say, available systems. And that is packbots or the remotely controlled construction systems or block systems or some military robots. And these were, how to say, the robots which were used for the different purposes. But so that is useful in some missions. So, but there is some kind of limitation because there are lots of, how to say, complicated missions which cannot be done by such kind of available robots. So then they try to modify the robot systems which are available, or they start to develop the new robot system which is specific to the, how to say, Fukushima decommissioning. And it took some time, but finally now some robots were already developed and used. So this is very special robots, but it is very useful. That is the difference between 10 years ago and now. And another question is the balance between teleoperation and autonomy. I think this is very the challenging issues. So what the TEPCO company requested us is to just, just give me some kind of devices which can teleoperate. they don't need any autonomous robot because they cannot expect autonomous robot to do any kind of tasks. So that is what they are saying. So, but in some sense, that is true. So autonomous robot can, how to say, operate only very limited environment. But in case of Fukushima, most of the area is unknown, and it is not guaranteed that the autonomous robot can work in such kind of environment. So maybe, but still, teleoperated robot, the edge should have some kind of knowledge. For example, if you teleoperate the drone systems, the stabilization of the robot should be incorporated in the robot. It is a kind of autonomy. So we should think about some kind of combinations. Some part of autonomy, it's better to be embedded.
Can I ask a question too?
Yeah, I think, yeah. We have not so much time, so
okay.
Would you give me a very small question?
Okay, so from your talk, I think it's a very problem of communications or software side problem, but how about the hardware side problems?
Hardware problems?
Yes.
You mean some kind of, how to say?
To modify the robotic arms or any other specification of the hardware?
Okay, so for example, for the ground vehicles, it should, how to say, climb up the stairs or go over the obstacles, or sometimes you should push some kind of object. And there are lots of functions needed for the robot when you consider some kind of unknown operation in unknown environment. And that is some kind of difficulty when you design the robot systems. So if you have one arm, it might be useful when there is an obstacle, but nobody knows if there is an obstacle or not. So that is very, as I say, tricky, but it is very interesting, but it is also very difficult for the designers to develop the robot.
I see. So unknown environment is the key factor of the. Okay. Thank you.
Okay. Thank you very much. You may have lots of questions, and I have also questions in Slido, but I'm sorry that, so I'd like to go on the next panelist talk. Thank you very much. So then, Professor Suzuki, the floor is yours.
Okay, thank you very much, Professor Sama. My name is Professor Shunichi Suzuki, project professor in the University of Tokyo. And 7 years ago, since I have been here in the University of Tokyo for 7 years, but before that, as Professor Sama introduced, I had worked in TEPCO and managing all of the R&D issues as a general manager. So the point is, so the most difficult problems for Fukushima Daiichi decommissioning is unknown unknowns. This is named by UK experts anyway. So this is really true things. But we engineers, researchers must find solutions. That is very important tasks. Now, what is the important things? Now, this is a time versus risk level. And this is, if we don't do anything, so the risk will be going up like this to the unacceptable zone. The reason is that, as you know, the explosion occurs. So the building and the equipment and the components had damaged. So, and the degrade, so with the time, all of the components and building will be degraded. So that's why Japan decided to retrieve the fuel debris from the reactor buildings like this. But point is that, you see it here, if we try to retrieve the fuel debris, the risk level will go up. The reason is that to retrieve the fuel debris, we must open reactor pedestal or reactor building. So that means we will have the higher risk for radioactive materials dispersion outside. So how to reduce those things is very important key issue. Now this is a reactor, but this is an operation floor. If you want to retrieve the fuel debris from the reactor from the top, in that case, we must install the machines and equipment on the operation floor. But operation floor are largely damaged at a very high dose rate. This is very different situation from 3 Mile Island in US. In 3 Mile Island, a human being can work here and can stand on. But in Fukushima, no one can stand on. So only a robotics thing, robots will be can work here. And this one is a fuel debris, and we don't know the properties clearly, and high radiation inside PCB and leakage occurs somewhere. So this one, it becomes a very, 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 we are facing a very difficulties. Okay, and as Professor Asama introduced, actually to understand what is the fuel debris, so by using a CLD rail and putting these robots, and finally found at the bottom of the PCB, PCB means a contaminated vessel, and they found that fuel assembled handle. What this means, fuel is inside here. So it goes down intact. That means because of the fuel debris, there must be a big penetration at the bottom of the RPB. So how to retrieve these things? And inspection, but not only robot inspection, but also inspection by muon tomography. And TEPCO found that fuel remains at the bottom of the reactors. So the combination of severe accident analysis called plant data analysis, the muon observation, and internal investigation by robots results allows the estimation of the location of the fuel debris of each unit. This is unit 1, unit 2, unit 3. So unit 1, most of fuel debris drop down on the PCB bottom like this. In the case of unit 2, most of the debris remains at the bottom RPB. Unit 3, just in between unit 1 and unit 2. So located in both ways. So how to retrieve these things? Maybe for the different units, so we must use the different technologies. The one of the point is that this one. This is the estimation of the fuel debris. So each unit is approximately 300 tons. That's a weight. Because the fuel melted with the components. So that's why the fuel debris amount becomes so large. So totally maybe around 800 tons. So how to remove such big amount? Now, what is important things for issues for fuel debris retrieval? First, these two red one is the most important thing. One is preventing radioactive materials dispersion outside, So dispersion of small particles during the fuel debris retrieving, maybe cutting the fuel debris, something like that. And the other one is the leakage of contaminated water. And second one is dose reduction to protect the workers' safety. These two is the main issue. And thirdly, don't take long time to retrieve the fuel debris, and preventing big criticality and the risk management, assuming accidents or failures. And this is, for example, to avoid the radioactive material dispersions, at first open the PCB. So PCB penetrations opening is very important things. So confinement function during a hatch opening or a remote operating hatch opening system must be needed. And as Professor Asama showed that this is ARM type devices to access to the fuel debris. This is a summary of these things, but there are many interfering objects. So method for removing interference objects is very important key issue. And also method for sealing work cell. So inflate seal must be installed and open the biological sealing work. This is also very important. And also verification of a combination of a robotic arm and access rail. And finally, a processing method effectively in terms of preventing diffusion of fuel debris. So a lot of things must be done, but those things must be done remotely, anyways, in somehow. By the way, this is our university's research right now, and actually environment structuralizations. This project is led by Professor Asama, and the construction monitoring platform for fuel debris retrieval by remote control technology. Because we must put many sensors, but as you know, the sensors is every year, the technology is becomes much more highly advanced. So, and also sensors cannot work for a long time inside PCB because of the high radiation. So first make a platform, and the platform on which camera and sensors can be moved will be built remotely, and the work status will be monitored, something like this. So like this, so this becomes a very good idea, and now the governments also think that this kind of idea is a very important key issue. Okay, what's that? Okay, so I will talk about the current alternative method to retrieve the fuel debris from reactors. There are three types to retrieve the fuel debris. One is the submersion top access methods, and second one is the partially submersion top access methods, and this one is a partially submersion side access method. So normally, this submersion method A is most profitable, a good way. So same as the TMI. But in Japan, we selected these two methods. So that means here they will be retrieved partly in water, but partly in air. Why? Because this is a PCB containment vessel. You see lots of hatch and bent pipe and penetration for pipes and cables. This seal, the materials of the seal is plastic materials. And because of the high temperature by accident, so those one must be damaged. So that's why. So if we want to fulfill the water, in that case, we must fix all of the sealing, but the hatch, bent pipe, penetration, the total number is about 200. So it's very difficult to completely fix it. So that's why we selected those things. But important thing is that the cesium 137 is the most famous radioactive materials, which emits a very high gamma ray. And this is the initial inventory. And 1/3 is absorbed by water treatment facility, but remaining 60%, almost 60%, still remains in reactor. That means very high radiation field. Now, for the fuel debris, when for example, if we want to retrieve the fuel debris from the top, in that case, at first, we must have containers on that. That must be remotely done. And then put the manipulator, something like that. And then get the fuel debris like that. But as I said, the amount of fuel debris is so large. So how long does it take if you use the manipulators? And the other big problem is that materials properties of fuel debris. Fuel debris is consists from metal, oxidizer, and boride. Boride is used as a neutron absorber in BWR, but as you see, the hardness, Beaker's hardness is so different. If you use a core boring machine, maybe oxidizer and boride is okay. But if you want to use the core boring machine for metal, something like a chewing gum, so because metal has a good elongation, so maybe it will stop rotating core boring. So depending upon the materials properties, we must select the tools ahead of the arms. So how to replace the tools in such a very high radiation field and also in very small areas with many obstacles. And then this is my idea, and this becomes one of the national government's research. But a large-scale fuel debris must be done a different way. That is solidify by using a cementitious materials, for example, and cut by wire saw, and remove it to the outside buildings, and here cutting by using cutting device and categorize the radioactive materials and then store in the casks in the stable condition. That kind of issue will be one alternative method for large-scale retrieval of fuel debris. So the important thing is that not only the current way, but also alternative method must be studied in future to finish safely and in short time. Okay, thank you for your attention.
Thank you very much, Professor Suzuki. I'd like to move on to the next speaker. And after the presentation of Matt, I'd like to have some break for Q&A. So may I ask Matt to start presentation?
Thank you, Osama Sensei. Hopefully you can see my slides now. So as Professor Osama said, I'm Dr. Matt Miller, the CEO of Createch. Createch is a company that's been developing and deploying technologies for the nuclear industry for around 11 years. What I'm going to do in my talk today is zoom in a little bit on a part of the process that has gone on over the last few years at Fukushima Daiichi, and really look at the robotic exploration task, because that's something that's quite unique. Actually, I think I might have got my slide timings on. Yep, sorry about that. So the situation at Fukushima Daiichi is very different from the plants that we're normally working with in nuclear. Actually, not because of the unknown unknowns thing that Professor Suzuki so accurately summarized, because that tends to be the situation in all obsolete nuclear plants. But what makes Fukushima Daiichi really difficult is the absence of designed-in features that enable us to get access, to visit, to inspect, and that we really have this whole site, which, going back in time 10 years, was all extremely difficult to access. It was all at least somewhat radioactive, so you had the difficulties associated with that. But as you can see in this image, also the explosion damage and the debris from the explosion damage made any form of physical access very difficult. And what we really needed to do in those early days was simply to understand what we were dealing with. So how much radiation is there? How damaged or not damaged is the building? How can we gain access? Which routes are clear? Which routes are not clear? And so on. And that really is the topic of of my talk today. When we began, we had already a toolbox of technologies that we could deploy for these purposes that we already knew how to use in other nuclear contexts. And in particular, we were using a device which we had developed for reprocessing plants, for decommissioning of reprocessing plants, which in many ways is the most similar use case to Fukushima Daiichi outside of an accident environment. So we had a device. It's sort of like you can imagine a large thermos flask, which is related to medical imaging instruments. So just as a medical imaging device like a PET imager will map the distribution of radioactivity within the human body, we designed a three-dimensional imaging device that maps the radioactivity within the environment. Normally that would be deployed through purpose-built access into cells in an operational nuclear plant. In this case, we didn't have that, and this was our first contact with robotics, really, in that we were looking at, can we take the same equipment, install it on some kind of crawler, and then drive that into the reactors to begin working out what the situation is. And so this image we can see here is quite similar to one of the user interfaces that Professor Osama mentioned in his presentation, and indeed that's because it comes from the same team. This is the Rosemary robot, which is one of the ones that Professor Osama highlighted on his slide of numerous robots. And what we've done here is to add on this kind of stripy black cylinder that you can just about make out in the center of that image. And that's the radiation imaging device, which contains a spherical optical image, a spherical gamma radiation imaging device, a 3D laser scanner using infrared light. And by moving this to numerous locations, capturing data and then fusing that data together, we could make three-dimensional maps and start to understand the situation. And that's what we see here. So on the left, we have a laser scan with overlaid colors that was produced by moving this robot around within one of the reactor buildings. So this is quite a large area that we're looking at here, tens of meters across. On the right, we can see the contamination map that was produced by fusing all of those data together and solving an inverse problem analogous to the tomography problem that medical imaging devices solve. So this is an estimate of fundamental physical properties of basically the number of radioactive atoms per unit area. And that's information that we can then use to simulate, answer questions, classify wastes, and really take control of the situation. The difficulty we had with that system was actually there's a lot of places that you just can't go. There's a lot of staircases that have become blocked by concrete debris. There's places where there's water on the ground. There's places where, for one reason or another, you just can't get something that big. And as long ago as 2012, we started to look at, was there a more agile solution? And we began to look at, can we use a drone to do this? The difficulty with a drone is drones can't carry the sorts of weights that we have with these instruments. Instruments are typically several kilos or double figures of kilos. A drone that you can fly inside can maybe lift a few hundred grams at best. So there was a real challenge there. You also have the challenge of how do you control the drone, because you don't have GPS indoors. And what we realized was there's one solution to both of those problems in the form of SLAM, so simultaneous localization and mapping, where a 3D sensor on board the drone is used to build a map and simultaneously locate the drone within the map. That solves the GPS problem. But actually, if we know the location of a radiation detector within a 3D model, and we can measure numerous locations, then that gives us all of the data that we need to solve an inverse problem and also do the tomography. So we could, by using SLAM, both do away with most of the weight of the sensor and solve the stability problem. Working with another UK company called Blue Bear, we developed a prototype drone system called Riser. And that drone system was deployed through a number of development flights at Sellafield in the UK, which is a large reprocessing plant. And that's what we see here. So here we're seeing a LiDAR map being built up, and this is all happening in real time. So the signals from this map building process are actually being used to feedback and close a control loop. At the same time, we're also measuring the motion of the system, and therefore measuring the motion of a radiation detector. We're observing how the radiation changes, and then we're using the laws of physics to interpret what that probably means about the location. And that's what these colors we're seeing here mean. So here again, we have an estimate based on what we've seen so far of what we think the most likely distribution of radioactivity is. And the more we move and the more places we visit, the more that map starts to come into focus and the confidence increases. And in fact, in this case, all of the radiation is coming out of these boxes in front of us. And as time goes on, the drone starts to understand that. So this is a system that gives us some kind of real-time visualization and understanding of the data that we're measuring. So we took this system to Fukushima Daiichi for the first time in 2017 and flew it actually in quite a number of places. But what I have here is some data from one of the first places that we flew it, which was one of the turbine halls. So this image on the right that you can see here is an isometric view of the internal contents of one of the turbine halls in black and white, with all of the structure stripped away. So the ceiling and the walls have been removed, and we can see the internal structures. Now, this is quite a huge space, over 100 meters long, something like 30 meters wide, and well over 10 meters high. And it was also completely dark, very difficult to access because of being essentially full of turbines and other equipment. Also, there was water on the floor, which we had to assume could be contaminated for safety purposes. And there's quite high radiation in some places. The building's also damaged by concrete debris that's fallen through the roof. And that's left to some trailing cables that were knocked down from the roof, and also fragments of steel reinforcement from the concrete that are dangling from the roof. So there's a lot of obstacles in here. In operating the drone, we could really only access the lower left corner here, where you can see the colored points which make up the radiation readings. Blue indicates not much radiation. So we were quite comfortable to stand for some time in this area. But as we moved further up the hall, it became a lot more radioactive and a lot harder to access. And that's why we were using the drone in this case. And you can see here from the colors that quite a lot of structure was observed in the radiation field. So there's definite hotter areas and cooler areas, and that distribution has a meaning. So we were able to work out from all this data quite a lot of what had happened in this area. This, for example, is a three-dimensional map of the turbines themselves, with a little piece of the ceiling isolated, and you can see various dangling components there. The drone was essentially, although I call it an autonomous drone because it was flying itself. There was a safety pilot present, but he was really not able to see the drone for the majority of the flight. So the drone was responsible for flying itself, but we did use high level decision making by people. So the drone would never move by itself except to avoid a collision. But the operator wasn't a pilot. They were simply saying, move forwards 5 meters, move right 3 meters, rotate 90 degrees, move up a meter. And the drone would execute those commands if it felt it was safe to do so. So you had this kind of low-level autonomy combined with high-level human intelligence, somehow collaborating to complete the job. So this is a very kind of detailed and specific example of how a mobile robot can be used to do exploration, but I think it adds, I hope, some a kind of a sense of what some of the applications that Professor Osama mentioned earlier were really like for the teams doing them. I think some other things to highlight is that actually Fukushima was really the inspiration for something here, which became very useful later at other sites. So there are things to be learned from this process, and the things that we've been doing to respond to the accident at Fukushima have taken the whole industry forwards in some sense. Another thing that I really found that I got from this particular application was the fact that robotics really integrates with a lot of other things, and it's very hard to say where robotics begins and robotics ends. And sometimes when you mix the robotics up with another domain, in this case, sensing or three-dimensional radiation mapping, you find a solution from robotics that can make the results of the other domain a lot more promising, a lot more applicable. And finally, I really think that the benefits of international collaboration around nuclear decommissioning have been very well demonstrated by Fukushima Daiichi. Not only has TEPCO benefited a lot from mature technologies that it could bring, but also other places have benefited from technologies that have been pioneered at Fukushima Daiichi. And I was particularly proud in this project because Sellafield in the UK put in a lot of time and effort and a lot of their resources to enable the development of this robot in an agile way in a controlled environment, such that by the time it came to Fukushima Daiichi, it was already quite a mature system. And I think that that's another really important lesson that we can all take forwards from Fukushima Daiichi for the wider global challenge of nuclear decommissioning. Okay, so that's the end of my talk. Thank you very much.
Thank you, Matt. So we are a little bit behind the schedule, but I'd like to have a little break here and accept some questions from front row. Are there any questions to panelists, Shunichi and Matt?
If possible.
Yes, go ahead.
Yeah, Matt, you mentioned the importance of the sensors. I guess that the sensors you need is typically a multispectral camera on board. And one thing I think it is also important is to be able to have capabilities for information processing on board. I mean, you will not transfer all the informations you would require. So what kind of thing you need to do on board?
So in that case, because that was an autonomous flying drone in a sense, so it was responsible for the control stability. Everything that fed into the control loop had to be running on board. We couldn't be relying on data going away, being processed, and then a control input coming back, because even a short interruption in communication would result in control instability. So in that case, the SLAM was running on board. All of the LiDAR sensor fusion was running on board, and also camera processing and IMU processing running on board. But the radiation data processing, which isn't really related to the stability of the robot, could be done in near real time rather than true real time, and that data was offloaded, and that's actually by far the most demanding computational task. So we have to effectively invert a matrix with hundreds of millions or billions of individual data points to solve that problem, and we have to do that once every 2 or 3 seconds. So we can't do that on board the drone, but that's okay because we're not reliant on that definitely happening.
Thank you.
Okay, thank you. So maybe you may have some more questions, but I'd like to move on to the last presentation of Gil. Gil, it's your turn.
Okay, thank you very much, Asama Sensei, and thank you everybody for attending this seminar. Let me share my screen, and give me just a moment here. Okay, so I'm Gil Pratt. I'm presently the Chief Scientist of Toyota Motor Corporation in Japan and the CEO of Toyota Research Institute in the United States. But I'm going to talk to you about work that I did when I was at DARPA after the Fukushima disaster. And so a little bit of the history, I won't spend much time on this slide because Asama Sensei did a wonderful job giving this in detail. But after the hydrogen explosions occurred, we sort of had a galvanic response in DARPA. And we put our heads together and the question was, what can we do? And so our first thought was, well, we have sponsored the development of many defense robots, maybe they could help. So as you heard before, the Thunderhawk, the PackBot, the Warrior, and the Talon were all one way or the other sent to Japan. And one of the interesting lessons about this is that the US Department of Defense actually responded very quickly and effectively to the disaster, but it ended up that using the Navy to send the robots over was too slow. And the way that they got there quickly was in the overhead luggage in a commercial flight. So I think that there's a lesson there in terms of disaster response and having things happen quickly. There's another set of lessons here as to kind of social issues and human issues. The Thunderhawk was used very effectively, and you see here some videos from UAVs that looked at the status, particularly of the spent fuel pools. The picture in the lower left is actually of Brad Towsley, who was the program manager in charge of the development of the Thunderhawk when we went to visit the site later on. But actually there was significant delay in the use of ground robots. And there was a rather famous blog that was written by one of the operators from TEPCO that ended up in the IEEE. I think many of you saw it. And I think that this is also a very important thing to consider. It's not so important now during decommissioning, but we spoke about, are we prepared for the next disaster? And I think the answer is no. And it's not only technologically that we're not prepared, but I don't think that we have straightened out the sort of organizational and human issues that caused this delay 10 years ago as well. And so in my next slide here, I asked the question, why? Why was there this delay in the use of the ground robots? The number one reason, and it's spoken about if you look in the history in that IEEE article and other ones, is kind of fear of failure. Generally, people don't like to fail, and using a machine that might get stuck, that might break, is a risky thing to do, and it's something that we need to think about in human psychology. Second, there was this big question of where are the robots? And in the Japanese press, we saw all kinds of misunderstanding by the public with phrases like, why don't we send in Asimo? And of course, research robots are not designed to be robust products. And there's this mistaken projection by the public, particularly if the robot is humanoid, that it has human capabilities, which is not actually true. And then finally, from the technological point of view, there was inadequate capability. So the rough terrain mobility was not good enough because it turns out that the edges of the stairs were rounded off. Manipulation strength and dexterity were lacking generally. And so the robots could be used for inspection, but there was actually very little that they could do physically. And in addition, usually communications is the first severe difficulty in a disaster. And this was particularly bad at Fukushima because of the radio frequency shielding effects of all of the reinforced concrete that was there. And so it's actually difficult to have telepresence work in such environments. And we actually just heard about that from Matt, even now with the UAVs, the importance of that comlink working well. So after we had this kind of mixed result in responding immediately to the disaster, at DARPA, we again put our heads together and thought about, well, what can we do to make this better? And this is actually the original pitch slide from 2011 when we began to think about, can we make this better? And here's a quote on the left-hand side, I'll just read it. Close study of the disaster's first 24 hours before the cascade of failures carried reactor 1 beyond any hope of salvation reveals clear inflection points where minor differences would have prevented events from spiraling out of control. And what this means is that there is still an opportunity for a future disaster for robots, if we do our jobs right, to intervene in a way to mitigate the severity of the disaster. It's really hard because time is very precious and not your friend, but I think that this is still true. And so with this in mind, for the reasons that are written up on the right-hand side, DARPA decided to go ahead and start a challenge-based development effort to try to improve the state-of-the-art of robotics for immediate disaster response. Here's a picture of a pitch slide that I used in February of 2012 that talks about the kind of philosophy that's going on here. And of course, this is very well known to everybody, but I think it's important to see how we were thinking. Of course, human beings normally operate in an environment. If that environment is contaminated by the green box that you see here, you can put them in a hazmat suit. That's the second line that you see here. And the first thing to do to improve on that, of course, is to decouple the human being from that environment by putting them in a safe place on the left-hand side, decoupling from a teleop robot that's in the contaminated environment. Well, that's effective to some extent, but human beings have a lot of difficulty with perceiving what's really going on. And we create predictive models inside of our heads, which you can think about as kind of like a digital twin, where we're imagining what's going on the other side, because typically the view that the robot gets is very, very poor. And a human being operating a teleoperated robot through a television screen is in effect creating a world model in their mind as to what's going on the other side. So the first thing that happens, as I mentioned, is that the communication environment becomes poor. That's what the arrow shows here over on the next line. And one way to try to solve this is to add some autonomy, supervised autonomy inside the robot itself, so that it can do some of the local work. For example, the kind of SLAM work that we just heard about, the local control for position control that we just heard about as an example. What the DARPA Robotics Challenge tried to do was to improve on this last line. And so the idea was maybe we can actually decouple the predictive model of what is going on over here from the human being and actually develop technology to make this whole thing work a lot better. And so I'm going to focus a lot on this particular idea because it was actually one of the key innovations that happened at the DARPA Robotics Challenge. So what did we do to make the challenge a simulation of a real disaster? Most importantly, besides the physical tasks that we gave the robot, which were directly inspired by the Fukushima disaster, we also tried to replicate difficulty in communications. And so our thought was that the amount of autonomy that you need in the robot and also in the human beings in understanding the environment is roughly proportional to the reciprocal of the communication bandwidth. So as the communication bandwidth gets worse, this denominator here gets smaller, the amount of autonomy that you need goes up. And that was our thought. And we're talking about autonomy on both sides, for human beings to have a model of what's going on in the disaster, and for the robot to have a model of what's going on inside of the mind of the operator. Here's what the particular structure of the challenge was, just as a reminder. We had a number of different tracks. The teams were funded pretty generously in some cases, and other cases, teams actually were able to join the challenge by themselves with their own funding. Some of the teams, 7 in the end, were given a robot. This was a Boston Dynamics bipedal robot, an Atlas, and 6 of the teams were funded, but actually developed their own robots with different topologies that they used, resulting in 11 funded teams and 14 unfunded teams competing for 3 prizes, $2 million, $1 million, and $500,000. We did the project between October 2012 and June of 2015, and it had a number of phases. The first one was this virtual robotics challenge, which we did in simulation, which was really effective. And this, again, moved forward the state of the art of real-time simulation. The second was a set of trials that was done in Florida in 2013, which was really focused on the robot hardware. And then finally, the finals happened in June of 2015, which was focused on both software and hardware. Here's what the trials results were like. This was where the focus was on hardware. And you can see all the different tasks here on the x-axis for each one of these charts and how many points the particular teams got on those different tasks. And you can see that amongst the more difficult tasks was driving the vehicle. Believe it or not, opening the door was actually hard, but many of the other tasks the teams did better on. And in particular, one team of young people from Japan, from the Shaft company, won that particular challenge and did the best. And so here, in a really fantastic turn of events, we managed to put together President Obama and the 2 leaders of the Shaft team for him to congratulate them in 2014. Let me talk about the finals a little bit. The finals were won by 3 teams, one team from KAIST from Korea, and the other 2 from IHMC and from CMU NREC. And what was really wonderful about this, first of all, they all learned from the Shaft team that had won the trials. And Shaft had actually gone on to be acquired by Google and withdrew from the DRC because they had more commercial work to do. But all of these 3 teams benefited tremendously from the work by the Japanese Shaft team that came before, and then built on top of that a whole bunch of software capabilities in order to do well. Here's how these teams did. This is sort of the general look at how they performed. And because driving was not actually done well in the trials, a lot of teams focused and learned to do it very, very well for the finals. But you can see that we actually made the challenge harder for other tasks. And believe it or not, things like stairs ended up being difficult, and getting over the rubble as an example. So it turns out that wall, stairs, rubble, and egress were actually the most challenging tasks that we had there. Communications. This was a hidden, but actually the most important part of the challenge. We had an incredibly extensive infrastructure for high-speed wireless communication between the robots and the operators, but then we had a throttle in between those 2. And that throttle was changed at different times. And so when the robot was outside of the building, the throttle was open. And then when the robot got into the building, we drastically reduced the amount of communications, and we made it somewhat statistical. So we tried to replicate as much as we could what we called the really bad cell phone connection between the operators and the robots inside the building itself. And so this is a record of the actual packets going back and forth for one of the teams as they went through the building itself and then came back out. So here's my last few slides. What came out of the challenge, I think most importantly, is both improvements in mobility robustness, in manipulation dexterity, but most importantly, this idea of how do you deal with a degraded communication link between an operator and the robot itself. And I'm going to use new terminology, which is now being used to talk about the technique that was developed for this. And what we did, what the three teams that worked, that did the best, they used digital twins, which was a real-time simulation on each side, where the digital twin on the operator side was keeping a model of what's going on in the robotic space of the robot and its environment. And the digital twin on the robot side had a model of what the human's intentions were on the human side. And what traveled over the communication link were not direct teleoperation commands or pictures coming back, but rather state updates that went back and forth between these two virtual worlds in order to try to keep them as synchronized as possible. And it turns out that you actually don't need that many bits that often in order to do it. So in general, this is, it wasn't a new technique, but I think that it was applied particularly well in the DARPA Robotics Challenge and distinguished these teams for how they made that work. Here's my conclusions. First, and this has been asked as a question also, it's important to realize that autonomy is hard. We've seen this in my own work now for Toyota in the automated vehicle space. Many other companies have seen the same thing. It's taking much longer to get that to work. If you have an unstructured environment in a disaster, it's even harder. And generally, it's not needed for these kinds of tasks. So there's plenty of budget available for human operators. Human intelligence and skill actually has no present equal in AI. Second, rough terrain mobility has gotten much better. There's been tremendous work over the last 10 years in articulated tracks and legs, UAVs, other sorts of robotic mobility, where I think it's not that the problem's solved, but I think our capability has gotten much better there. However, in manipulation, there's still significant work to do. The strength of the robots we have, the dexterity that they have, still needs significant improvement for the robots to do things other than just look. Looking is important, but it's nice, especially in the initial stages of a disaster, to actually be able to affect the environment. And human manipulation, particularly the way that we use tools, is still typically much more effective than the robots that we have that are out there. And then finally, effective control can be achieved, as I just showed, in degraded communication environments through the use of synchronized digital twins and local control happening on each side of that bad communication link. And I happen to have had a discussion recently with Professor Khatib talking about his actual significant evolution of that architecture into haptics. And he's done a whole bunch of really neat things. So I think that there's a beautiful field that's emerging about how to do telepresence in a much more effective way. We did not use haptics at the DRC. The teams just looked at pictures and then had joysticks trying to tell the robots what to do. I think that haptics is a significant advance in that. So with that, let me stop. And I also had the privilege of several visits to Fukushima, one on the left with all of DARPA's management, which was fantastic. And then on the right-hand side, a little bit after, with Professor Vijay Kumar, where we actually got to go inside of Unit 5 and see the actuators for the control rods that are under there and get a real appreciation of how confined things are in the reactor buildings themselves. And this is for a reactor that was not damaged by the disaster. And so, of course, things are much, much worse where there's melted fuel and debris all over the place. Thank you very much.
Thank you very much for your excellent talk, Gil. So the time is almost the end of the colloquium, but I'm very sorry for my, bad time management. But I'd like to propose to extend 10 minutes more for Q&A and discussions. So I'd like to accept some questions to Gil or other panelists. Keiji, do you have any questions?
Yeah, I have one question to Gil about I believe that the poor communication situation is very important for for using disaster response robots, and I think that the DARPA disaster challenge situation, I mean a very low communication bandwidths seems to be too tough, actually. So in the real disaster situation, I think the longer wavelengths is required for the better communication, but the longer wavelengths requires becomes a low bandwidth actually.
Right.
So in this case, how do you think about such kind of situation? I mean that between the too tough or the too easy.
So I agree very, very much. And we actually tuned the toughness depending on the team's response. So we didn't want the communications to be open enough so that all the teams did well. And so we kept throttling it back. And we met with the teams several times and had even mini trials before the finals in order to check how low the communication should go. I think that you're right. I think that in some disasters, the communication is not as bad as we made it out to be. But you're also right that as you increase the wavelength and decrease the frequency in order to get better range and reliability, naturally the bandwidth tends to go down. So that's a factor too. The other option is a mesh network of wireless access points that is deployed in real time at the disaster. And I know that some researchers have worked on that too. And I think that that could help.
Yeah, thank you very much.
Thank you.
Thank you. Jennifer, do you have any questions to any of panelists?
Yes, so I was thinking like from moving from simulation to the real world, what do you need to qualify the robot, like certify the robot? What are the validation or verification of the robot is done before it's actually put into the nuclear place? Yeah, anyone can answer.
Let me give an answer that's from a point of view of just the initial disaster response. Disasters are very infrequent. And as a result, having robots that sit around and gather dust and aren't used and then are suddenly needed and deployed for a disaster is not a workable answer. And so one of the potential answers for disaster robots, and Professor Murphy is an expert on this, is to have them have dual use, that most of the time they're used for some other purpose, for instance, responding to car accidents, things like that, or house fires, and then they can be suddenly put to use in a disaster. But it's very hard, and you're right, you have to certify it, at least for the initial response, for a unknown, right? I would love to hear from Matt or others in terms of the decommissioning part. What is the corresponding certification that needs to happen?
Thank you. Well, okay, go ahead, please.
So with that specific flying robot, I think it's quite an interesting piece of learning about the validation, because we did it initially the nuclear way, where a lot of engineers sat down together and tried to work out what are all the things that might go wrong, what are all the things it has to do, what are the tests for all of those, and put together a validation and verification program for it, and put the robot through that sequence of tests. But then what we also did immediately afterwards was an agile approach, where we took it to the real environment, always the real environment, but progressively more extreme versions of it, and tried it out. And what we found out was we hadn't got our validation correct. It passed the validation, but we'd asked the wrong questions. And we much more rapidly ended up with something that actually worked when we just got on and used it. And I think that is really an extremely important piece of learning for nuclear decommissioning in general. There's just no substitute for experience.
Thank you. Robin, do you have any comments on disaster response?
I think all of the comments that have been made, the insights are just wonderful and reinforce what we've seen at over 30 other disasters worldwide. And particularly Dr. Miller's comments about getting in there and understanding the work domain. is, which includes both the physical characteristics as well as the operators and socio-technical system, is so key to, I think, the future of robotics, being able to make that difference, particularly at the very beginning.
Thank you very much. And we received many questions in Slido and also chats. Questions are all very, interesting and also very important. But I'm very sorry that I cannot pick up all the questions. And there is one question about the dumping of nuclear radioactive water into the ocean. And this is quite a new news. And it is really difficult as a problem, I think, because it is not just a technical problem, but also social or political problem. So it might be difficult to answer these questions in this colloquium. But Suzuki Sensei, do you have any comments on these questions? I read the question. Recently, Japan plans to dump nuclear radioactive water into the Pacific. Do you think this action will influence the research on marine robotics? So,
well,
yeah.
Let me show some of the systems, first, and then I will answer later. Okay. Can you see this?
Yes.
This is a conceptual diagram of reactor circulating systems, and the water is circulating here, and then the radioactive materials was included in this water. And finally, two systems removed the cesium and strontium, and after desalination system and strontium treated water here, and then after that, this multiple nuclide removal equipment that is called, in short, ALPS system, and that removes 62 nuclides. But only one nuclide cannot be removed. That is tritium. So tritium is it's a H3. It's very similar property, physical properties, chemical properties as water. So it's very tough to separate these things. So the Japanese government do a lot of research about this, collaborated with many countries. And actually, geospherical injection system and discharge to the sea, and the vapor release and hydrogen release and the underground burial. And this one was tested. And then finally they decided number 2 and number 3, discharge to the sea and vapor release is the most appropriate way. And actually IAEA accepted this idea and concept, and this is a reasonable methods. But if we have the vapor release in that case, we must understand because the vapor is always affected by the temperature and the weather, and then it's very tough to control. But instead of that, the discharging to the sea can be controlled if the ALPS system works well. So monitoring those systems is very important key issue. Right now, the tritium the level is a very low level because that is a 1500 becquerel. That is a 1/7 of drinking, and the limit of the tritium for drinking water by WHO. So the concentration level is very low. So the tritium itself is not so big problem in that sense, but as and also compared with the other countries and power reactor always discharge the tritium water, and that level is very similar or much more bigger in some power plants. So the point is that what's the difference? The difference is that this material, this tritium used to be this is caused by the accident. That means originally contaminated water includes a lot of nuclides. And then ALPS works, if the ALPS works well, in that case, only tritium and tritium maybe will be well controlled. So that means monitoring of the ALPS system is very important key issue. So I think that the water marine system robots, maybe, of course, to verify the tritium amount in water, that will be done somehow. So in that means water robots can take a sampling, can do a sampling and to show that, but maybe it takes a couple of weeks to get the results actually. But that kind of things, robots can be used. But the important thing is that the monitoring of the system itself, and also show the results open to the public, especially including international society. That is very important key issue, I think.
Thank you very much. I think the monitoring and also sampling is very important for a robot system to perform, even in the case that so this kind of discharge will happen. So Matt, do you have any comments on this kind of questions?
Well, they're very difficult questions to answer because, of course, they're not purely technical, but also social. I think speaking as as an engineer who's looked at this and is sort of comfortable with my understanding of radiation, I understand why this is a responsible thing to do. But of course, it's very natural for people to have concerns about it. So I think I agree with Professor Suzuki's point that actually demonstrating the monitoring and the control and that it's being done in a responsible way is going to be critical.
Okay, thank you. So I'd like to pick up one more question. So it's from Julio. From this experience, are we getting some indications on how to modify the design of potentially dangerous infrastructure to make them more robot friendly? So I think the current nuclear power plant is not friendly to even human, but but for robot, it's really not friendly. So I think the idea of environmental structuralization, which was mentioned by Professor Suzuki, this kind of concept is very important. We can modify the structure of plant or infrastructure for the robot to operate easily. So do you have any comments on this kind of things? Nagatani-san, you are also the expert of the disaster response.
Yeah, so I'm also working on the maintenance of not only the such kind of plant, but a bridge or infrastructures. So these kind of things are also not good for human and also not good for robots. But it's understandable because the such kind of buildings or plants are made in early 1960 or 1970. It's very old structure. So we have to actually modify the kind of not reconstruct, but add something or add attachment of something for the robot. It's one of the good solutions, I think.
Okay, thank you very much. I extended 15 minutes. I'm very sorry that it's very late. And I really thank all the people who ask questions and send us the comments, and they are very important Finally, but I should stop now. I'm very sorry for that. I could not pick up all the questions here. So maybe I'd like to wrap up to show my last slide. Okay, so it's a kind of take-home message. And the problem is how to respond to nuclear disasters or decommissioning. But it can be, has a general question is how to respond to disasters. As Gil mentioned, so when this happens, we should respond quickly to the disasters, and we should grasp what happens in the disaster sites, and then we should respond quickly. So it is very difficult problem. So there are lots of technical challenges. So it is very good, problems to consider for roboticians. And also we should think about usability at the sites. The robot system should work at the sites, not in the laboratory. So it should be very practical. And also we need some kind of continuous efforts to realize this kind of functions. And I think the disaster response robot may not make a very big business, but the humanitarian viewpoint is very important. And also, as Matt mentioned, international cooperation is very important because disaster does not happen so often. So we should gather the wisdom to derive the solutions. So finally, okay, so I'd like to thank all the panelists and the front row to participate in this colloquium and have a very exciting discussions. And also, I'd like to thank all the participants to this colloquium. And finally, I thank the organizers, Professor Osamu Khatib, Professor Paolo Dario, and Professor Yoshi Nakamura, or the organizers to have this to arrange this opportunities. Thank you very much. So I'd like to stop the colloquium now. Have a nice day. Bye bye.